extra CA0. Yes, I lost the CA0. Sorry. If the expression I had up here, I have to go back to that expression. And I'll put the CA0 back in. Remember, I had KT was equal to an integral XA of 0 to XA of t dxa over 1 minus XA m minus XA. But I also had a 1 over CA0 here. And I lost this while I was carrying along. So that CA of 0 should have been CA0, should have come along. I should have that CA0 over here, in which case these would cancel, in which case there's no CA0 here. That's gone. There's no CA0 here, and there's no CA0. That's the correct answer. Any questions? Okay, so what we've done so far is we've used the integral method of analysis, both with CA and with XA. And we looked at first order, second order. So first order reactions, second order reactions, zeroth order reactions, nth order reactions. We noted here we did A plus B goes to product. Remember, when A plus B goes to products, the rate RA, we said, is minus K CA CB. And we looked at the case M equals 1, and N was different from 1. We looked at the case where this is equal to 1 and not equal to 1. I want to note something. Let's say I look at the case 2A goes to products. What's the rate expression for 2A goes to products where there are no A's in the product? Who was that?
Oh, I say it's RA is equal to minus 2K
CS. I want you to notice we've actually solved this one already. We did it in terms of CA when N is equal to 2, but we also did it in terms of XA. Why is that?
I left out the 2.
In the case when M is equal to 1, M is equal to what? If you remember, I had up here, of course it's never convenient to erase too much. I had CB0 XB was equal to CA0 XB. So remember, this is the amount of A I used up, this is the amount of B I used up. If I start out with the same amounts, and I use up the same amounts, then CA equals to CB. So in the case M is equal to 1, this is equivalent to saying CB is equal to CM. Okay, so this expression that I had, this one, for M is equal to 1, is also, if CB is equal to CA, then this is minus K CA squared. So the only difference between this and this is the factor of 2. So in order to get this answer, I just have to stick a 2 in front of the K, and I get the answer. So we've done that case. Okay, what else would I like to say? Let's talk about something known as the method of half-lives. Yeah, let's talk about the method of half-lives. Okay. If you remember, we spoke about a few methods to figure things out last time. We spoke about the method of excesses. We spoke about the method of the stoichiometric ratios. And I don't remember if we spoke about the method of isolation. Did we talk about the method of isolation? Okay. Isolation is, let's say I have a bunch of species, so I have A, B, C, etc. goes to R, S, T, etc. And I don't know what these stoichiometric coefficients are. In fact, I I don't know which species, I don't know the stoichiometry yet. I don't know, I'm sorry, I know the stoichiometry. I don't know the kinetics. Why don't we say that? So I know I'm trying to figure out a rate, and I have a CA to some power. Did I use Greek letters for the stoichiometric coefficients? Okay, so let's make these Greek. Rho, sigma, tau. CD to be etc. If I want to see, one thing I can figure out is A zero or non-zero? Or does A even, should A even appear here? One way is I could try to run the reaction with no A. I can throw in B, C, D, and if the reaction still runs, then A isn't required. If A is required, so that's how I can figure out if A is required. So if there even should be a CA. And then I could try to run the reaction without B and see if B is required, if the B reacts. So that's the method of isolation, take individual things out. But I'd like to talk about, we spoke about in the method of either excesses or stoichiometric ratios. In either excesses, the method of excesses, we made B, C, D, etc. very high concentration. So they were constant, and we were solving an expression, RA goes like CA to the N. In the method of stoichiometric ratios, we were solving an expression, RA goes like CA to the A plus B, which is equal to CA to the N. You guys keeping down? I'm trying to have a class here. Okay, so in both of these cases, we had the rate goes as CA to a power. And we looked at the differential method analysis of determining this. We did a bunch of reactions, we calculated initial slopes. How do we do this in terms of the integral method of analysis? The same type of experiment, how do we analyze it? So what we see is if we're solving RA goes as CA to the N, or CA to the A, we already integrated that. Here's the expression. So we have, let's rewrite it. I have CA of 0 to the 1 minus N minus CA of T to the 1 minus N is equal to, I flipped them so I won't have to worry about the minus sign, 1 minus N KT. Or actually, it doesn't really, I can put the minus sign back, I can put the T here and the 0 here. And then this is N minus 1. Okay, so let's look at what's called the method of half-lives. Remember, what I'm trying to do is I'm trying to determine N in these experiments. N is unknown. So I'm trying to determine N. So if I wanted to determine N, give myself a little space here. Find N. So again, find N. And let's try the method of half-lives. And by the way, this is where N is not equal to 1, this expression. This is when N is equal to 1, this doesn't give me anything of interest. So what's the method of half-lives? The method of half-lives, I say, let's try to react the system. Well, for each CA of 0, react system until CA of T is equal to 1/2 CA of 0. So then you make a plot, you have a table. You've got CA of 0 and T 1/2, the amount of time it's taken to get time needed to get CA of T equals 1/2 CA of 0. Now, why is that useful? Well, let's plug in CA of T is 1/2 CA of 0. So I have CA of 0 to the 1 minus N over 2 to the 1 minus N because this is a half of that, minus CA of 0 to the 1 minus n is equal to, well, I can factor out the CA of 0 to the 1 minus n. Times 1 over 2 to the 1 minus n minus 1 is equal to n minus 1 kt. And this is not just any t, but this is t1 half. Okay, so let's rewrite this. I've got CA0 of 0, 1 minus n times the log of CA of 0. So I take the log of this, and I bring this thing to the other side. So I have, that's equal to the log of n minus 1 k over 1 over 2 to the 1 minus n minus 1, plus the log of t. Did we do that right? I did a lot of steps there in one. So this thing, I divide by that. Yeah. And I have 1 minus n log CA of 0 is equal to that. Okay, so now I'm going to divide by 1 minus n. So I've got the log CA of 0 is equal to 1 over 1 minus n log n minus 1 k over 1 over 2 to the 1 minus n minus 1. Plus 1 over 1 minus n log t1. What does this tell me to do? This is of the form y is equal to mx plus b. It's in the form of a straight line. So what does that tell me to do? This says if I plot I make a plot of the log of t1 half. Remember, I measured. I have t1 half and I've got CA of 0 versus this thing, log of CA 0. This predicts that I should get a straight line of slope 1 over 1 minus n, and the intercept is equal to this thing. So what does that tell me? Remember, I'm doing a set of experiments. I take a bunch of beakers, and I have different CA of 0. I have a bunch of beakers, or a bunch of hatch reactors, each one with a different initial concentration. And I take my stopwatch, and I let each one react until the concentration is half of what I started. And I note down the CA of 0s, and I note down the T1 halves. And then if I make this plot, log CA of 0 versus log T1 half, the slope will immediately give me n. And once I know n, I look at the intercept, and from this formula, the only thing I don't know is k. And as long as n is not equal to 1, that is, when n is 1, this will give me an infinite slope. So I have to do a separate test to see if it's n is equal to 1. So n times up, but this is how you would determine n using the integral method of analysis. We have the solution already for n is equal to 1, so I can just write down that test as well. And then we said for n is equal to 1, CA of t over CA of 0 is e to the minus kt. If I did the same experiment, then I have e to the minus k t1 half is equal to CA of 0 over 2 divided by CA of 0. So this is just a half. So you can easily solve for T1 half here. T1 half is just minus log 2 over minus K. Log 2 over K. So this is n equals 1. When n is equal to 1, you get K, actually I should write it the other way. K versus T1 half. But if I don't know n, and n may be different from 1, here I get both n and T1, n and K. So I get n from here and K from there. Are there any questions? Okay, I'm going to put some homeworks in my box after the class, right outside my door. I still have to photocopy. So I will photocopy. Are there any questions?